Okay, I think we can get started. People are coming in. It's my pleasure today to welcome Pavel Tiunov, who is discussing design decisions behind CubeStore. Pavel has a PhD in computer science and has been working on analytics and BI tools for more than 15 years. He's a co-founder and a CTO at CubeDev, the author of Cube.js and CubeStore, and is an aspiring Rubik's Cube solver. So Pavel, thanks again for doing this talk. I'm going to hand it over to you and take it away.
Yeah, thanks, Robert. Hi, everyone. Yeah, today I'll be talking about CubeStore design decisions. CubeStore is a pretty new thing, and it's basically a part of a cube stack. And this is basically materialization layer of a cube itself. And for those of you who are not familiar with a cube, basically it is analytics API for data apps, obviously open source. You can visit our website to see more on it while you're listening to a presentation. Yeah. So yeah, let's get started. So myself, again, yeah, I spent over 15 years in enterprise software development and analytics, building BI tools like a lot from scratch. And I co-founded CubeDev, the company behind CubeJS, and basically was a original author of CubeJS and CubeStore. So I'll be talking mostly of stuff with like I was writing myself and working hands-on a lot. So yeah, let's talk about problem. And like in general, this I would say this presentation was designed to and planned to be like really like deep dive into the problem and into solution, but really it's just we'll do an intro to the problem and some like design decisions sneak peek, because it's not enough time. It's so much to like to tell about the CubeStore, so we don't have enough time. But let's start with an intro and just talk through some of particular design decisions behind CubeStore. So user-facing analytics, and for most of you who participated earlier talks, I guess it's very familiar stuff. But just to reiterate what it is it like user-facing analytics? So it's as simple as you have users or customers, and they're they want to analyze their data in and basically store data for them, like customer data, doing analytic queries to your app. And then basically the same app and is a special, I would say, user experience expectations at the end. So it should feel native, and it's usually should feel like almost like in a consumer app in many ways. And because of that, like user-facing analytics is quite different from all other analytic domains, I would say. So a typical example of it is Uber Eats. So Uber Eats has restaurants as their customers, and they're on a platform of Uber Eats, and they can see their analytics inside Uber Eats app. It's something you don't see as a consumer, but restaurants can see it, like to see how their business is performing, basically. Yeah. So, and I guess you're quite familiar with this concept. And so let's talk about how like this customer-facing analytics data apps can be built in general. And I tried to basically go through all the history of how these tools evolved over time. And the first one, and it's historically like really the first one, is pipelines. And I guess some of you are familiar with that concept. And so the idea is quite simple behind it. So if you have like multiple data sources and you want to bring them to the user as a user-facing analytics, you just build a pipeline. So it's usually every query is a different pipeline and can connect data from different data sources in a really variety of ways. Can run any machine learning stuff or just simple join operations and bring it all together after processing to key-value store, something scalable like DynamoDB or Cassandra or any other like really highly scalable key-value store. And the client just queries this key-value store to fetch exact results of a query which were calculated just beforehand. So, and basically analyzing all these approaches, we did this some small criteria table. So we think it's really important criteria when you build like user-facing analytics. So the first one is basically what data size you can process. Is it limited in any way at this point? And for pipelines, it's usually not. So it's really great in terms of like data size and data scalability. And another one, which is quite important for user experience, because from customer-facing side, people usually expect actual, I would say, consumer experience. So, and this is sub-second query latency. And in pipelines, you can do that because you usually pre-calculate all the data in pipelines. I mean, all the aggregation part of it. And also high query concurrency is also supported in this approach because so key value sources is highly scalable stores. So you can like distribute data very well there. And also low ingestion latency in case you're using real-time pipelines. So it's achievable as well. So there is no problem with it in pipeline approach. And however, so as you may develop this stuff and you'll find yourself that pipeline maintenance cost is really high. And also in terms of data replace, if you need, for example, to change some schema for like to redefine definitions of your business metrics, is cost is quite high for pipelines. It's really in some ways even not feasible to backfill the data. For example, Google Analytics is very well known example of it because Google Analytics is built on top of pipelines. And for example, if you redefine definitions of custom metrics, you cannot backfill the data. They just don't support it because it's not quite feasible. So those two are really cons of pipeline approach. And the last one, but not least, join support. Again, joins are really well supported by pipelines if you do them in the pipeline itself. So no problem with it. Yeah, so going forward, as a lot of database evolved and we started to see a lot of so-called time series databases. So those are basically designed to store time series data and very like specific databases. So those are Elasticsearch, Timescale, Influx. They're very different in approaches, but I tried to group their pros and cons together. And if you'll see the same table of this pros and cons, it's basically in terms of data processing amount, some of them quite maybe it's quite unlimited in terms of how much they can process, but they are very restricted in terms of it should be time series data. So you cannot do any data in terms of what you can store there. So if you don't have time dimensions, it's really tricky to do. And yeah, and it's really great in terms of sub-second query latency. Time series databases are designed to serve real-time workloads, and in terms of query concurrency, some of they do it, some of they do not, and it depends a lot on queries they use. For example, like timescale is much more advanced in that type of use case because they use this materializations just before the raw data sort. So different databases have different trade-offs here. And they're really great in terms of low ingestion latency because they designed to be like really real time here. And again, low ingestion pipeline maintenance costs. There's basically no pipeline in front of time series database because all the data flows into database itself, which is really great, and no additional cost on data replace. So if you need to change your schema in some way, it's just a different query, so you don't need to do any pipeline replace or anything like that, unless you're doing materialization or on the side of time series database. However, in terms of join support, it's very limited, and not every database supports it, and it's very limited in terms of scaling for all time series databases. So it's really tricky to do. Yeah. So yeah, the next one approach is if we go with our web data source, and basically today it's been really a lot of talks about specifically this type of data source, which is usually Pinot, Druid, ClickHouse. And those data stores basically in many ways designed for this use case. And the typical approach here, if you go with this OLAP data store approach, you basically have a lot of data sources, and you have usually you have batching pipeline, and you have streaming processing pipeline, which all pump into this like one big OLAP store. And the thing is, you at this point, like for example, joins or any other transformations, or like any transformations at all, should be done for usually for two pipelines in very generic case. So it should be done for batching, it should be done for streaming processing, and you should put it like in one single place. And this approach is, I would say, evolution of pipelines, and it's very, like in terms of performance, as you may see, it's quite the same. So it's really like no limit on any data size, no limit on a concurrency and a query latency. So it's really highly scalable, and in terms of ingestion latency it's really good as well. And but still, as in terms of like pipelines and data replace is a little bit better, but in terms of this cost, you take the cost here because and it's because mostly like this part is duplicated, right? So you should support and maintain pipeline first of all for I would say one per table. It's usually per rollup table, in some cases per query, and you should support multiple versions of it for streaming and batching processing. So those are different. For this purpose, for example, Uber developed their own like SQL dialect that used in both in Spark SQL, compiled to Spark SQL, and Flink SQL. So this data processing can be like centralized in terms of descriptions, but still it's really still high, but like in terms of cost, still high cost, but much better than I would say than pipelines, and replaces much better than pipelines. However, you still would need to do some extra work if you want to backfill all the stuff. Yeah, and I would say the another one approach that I wanted to discuss is, what if you use cloud data warehouse actually? And this was originally wasn't designed to do any like user-facing analytic stuff. It was designed for BI workloads, but like in general ecosystem around cloud data warehouses, the tools we have there, and it's like ELT approach, like transformation in warehouse, all the DBT stuff. So a lot of users like it, and Cube was organically started in this domain, and we basically, as we figure out, and we tried basically to build the solution on top of data warehouses. And build like user-facing analytics API layer. And as we moved on, we figure out it's actually, as it like today was previously discussed, cloud data warehouse is not really was designed for this problem, and mostly because data warehouse is really unlimited in data size, but like in general, it wasn't designed to provide any like really low query latencies or either high query concurrency, and it wasn't also designed for low ingestion latency, like for any real-time use cases. But in terms of like user experience, people get in data warehouse is like really great. So all the CLT movement, we really like that, and basically built Cube around this movement. And so everything is SQL, every data is accessible within SQL. So, and there was a lot about this one today. So, and it's really great. So really low ingestion pipeline maintenance cost in terms of it's just like you're changing SQL and your pipeline was rebuilt. That's it. And in terms of data replace, it's really scalable. So like data warehouse is really great regarding data replace. Nothing special should be done. If you materialize something, you just should rematerialize it, and that's it. And the same stuff is joins. So I guess there is no limits on the join imposed in data warehouse. But as we moved on, still, I would say those three problems are major for providing really great experience for user-facing analytics. And we figure out that what we can do at that point. And the solution was an idea was, can we just enhance cloud data warehouse and can be as performant as a lab store, but save original cloud data warehouse user experience, developer experience. And basically in terms of criteria, can we bring those three criteria up to speed? It's a sub-second query latency, high query concurrency, and low ingestion latency. And we started to think about how we can come up with it, and we basically analyzed a lot of different solutions in terms of OLAP stores as well. And we decided go and basically build our own Cube store layer at that point. And I basically describe a couple of words why is that. So and in terms of how this one is structured, and what is basically idea behind it. So so as a typical example of data warehouse, you have LT layer, which pumps the data from different data sources right into the data warehouse. You are using the pretty same tools as you're using right now, and for data warehouses like any transformation tools like DWHs there. So and this gets your batching part for data processing part the same way as it done for OLAP data stores. But for real-time subscription, you're using some streaming processor for example, KCO, Kinesis, or Flink, and so you're doing like real-time ingestion at that point to this real-time streaming processor. And KubeStore subscribes to all of that stuff. And KubeStore basically do not fetch and load actually raw data from the stuff, but only so-called rollup tables, so aggregated tables. So all the heavy lifting is done on data warehouses side and streaming processor side. So KubeStore is really thin storage layer to do like joining all the streams together using Lambda union query, if you're familiar with this Lambda architecture. And basically allows you to serve all of this data right from data warehouses and streaming processors in real time. So this was basically an idea, and we started to think about how we can basically develop this stuff, and we came up with multiple requirements that we need to fulfill in order to be able to do this. As it's usually we wanted to make it highly scalable in terms of data inputs. So even aggregated tables, they're really small in size, but we aiming towards billions of rows as an input. It's usually, so if you have billions of rows and aggregated tables, usually you have hundreds of billions as an input of like in a raw data, which makes sense for us. And again, requirements from previous tables, it should be sub-second response time and high query concurrency. This one comes from basically user experience that required for user-facing analytics. And another one requirement is that input data always should have primary key, and this one helps a lot for sorting the data, and it's basically a consequence of like the data in fact is always aggregated. So we're using only rollups as a I would say source data for KubeStore. So we never pull the raw data from the data source, and it should also support batching and real-time streaming data sources, so we can make it really like real-time, so and really like real-time experience for users, and it's the same as a criteria table. And also it should support join between the sources. This one is more about like data federation stuff. So and this is the architecture we came up with to fulfill these requirements, and those basically really high level. So KubeStore itself is highly distributed store. So we have router node which hosts like high throughput meta store and responsible for query planning, and splits all queries using shared nothing architecture into like small subqueries and send it to worker nodes, which use distributed FS like as a storage layer, and worker nodes ingest ingest the data directly like from data warehouses to distributed storage layer, and we use Parquet as a format. And basically this one is also accompanied with like cache for map function that allows you to query data which is local for this machine, so we don't download data while querying. This one like really high level, and there are multiple major design decisions we've made in order to basically accomplish and fulfill these requirements I just talked about. I won't be able again to describe all of this stuff, but just a high level sneak peek on this one. So first of all, we figure out that we need high throughput metastore. And this is because we analyze a lot of data stores, and we figure out that many of them start to basically lag whenever there are like a lot of tables inside those. And we thought that it will be great to support like a lot of like tables in terms of in one data store, to be able to support really like a lot of partitions that make it like really highly distributed. So we are aiming towards really highly scalable metastore, and we decided to use RocksDB as a metastore layer here. So this is the first one. The second one, we decided to go with the concept of indexes that like should be like sorted copies, and this trade-off is basically based on the decision is we want it like KubeStore to be highly materialized as much as possible, and many OLAP data stores uses pretty the same concept, but the idea is so we resort the data for each query, so it's compressed, optimally compressed for this particular request. Also, other one is quite standard for many like query engines, so it's after partitioning, so you don't need to think about partitioning at all. So done behind the scenes. Format is a Parquet. It's quite standard to see it like as a columnar storage format. And we use distributed file system as a storage layer, so this one is no surprise, and like S3 and GCS quite standard, and also HDFS for such type of applications. And we try to use shared nothing architecture as much as possible. So there are like mostly like KubeStore is shared nothing in a way that like nodes don't talk to each other. And in terms of like real-time support, we designed it to be like in memory. So if you're familiar with that, so there is a problem to writing like columnar data structures like in memory, and how to basically compact them. So this part of thing is in memory. And we introduced collocated join indexes to make this join is basically possible. So in terms of tools, also we decided to not move to like from scratch, and there is like great tools like Arrow and DataFusion, which are built in Rust. So it's Arrow Rust implementation. And basically, if you're familiar with that, Arrow is a columnar processing, like I would say, library, in DataFusion is a query planner and SQL execution engine provided as a library. So those are two huge shortcuts to what we are doing, like in KubeStore, and basically most of heavy lifting were done in these libraries. And again, RocksDB is a metastore layer. So for those who interested, like as a deep dive, I provided this like basically metrics you can review. I would say offline when we share like slides. So I have only 5 minutes, and I'll try to give you like really sneak peek, and we'll go to the questions on some like design decisions that been made. So again, I would say that in a couple of weeks from now, we are going to release like highly detailed article in our blog about how the cube store is built and why we decided to go this way. But this one, you consider like really sneak peek to that article. So yeah, so real-time in-memory chunks. This one, again, as I already described, is to act as a buffer between single row writes and a Parquet. So if you're familiar with the Parquet format and like columnar storages overall, you couldn't write there like line by line. It's basically a lot of overhead for any columnar structure, and that's why all the columnar storages have some sort of batching. And this like buffer for us is like in memory chunks, so we store them in memory. And the thing is, when stream ingested, we store each memory chunk on a partition owner worker, and then basically every minute those are compacted to persistent storage. And so if you can see this routing diagram for a memory chunks, is basically here we have the router node and the worker node, which works on the streaming ingestion. So this is streaming subscription job is usually connected, for example, like to KSQL, and it's streaming serves directly to worker nodes, which will serve workloads directly. And then when query comes in, it's actually using like shared nothing architecture, and query splits between these worker nodes and goes to node 2 and node 3, and this partition and in-memory chunks are merged at query time. But it's a really simple operation because it's in-memory chunk. First of all, you don't need to read it from disk, and it is also like quite small usually. And those can be merged together in flight and returned back to users again. So this is like highly distributed. You have like a lot of nodes here. And so this one is basically, I just started to describe this, and let's see like in memory dive, deep dive to shared nothing architecture here, and basically what's used to fulfill the query in general. So, and again, the concept of shared nothing architecture is basically worker nodes never communicate with each other, and this is basically allow you to like cut the traffic between nodes and really no networking like communication involved in the query processing, which allows you to like make it really highly concurrent at this point. So, and router node also do not fetch raw results from worker nodes. So this allows to cut communication between router and worker nodes as well. So it's really compressed in terms of like traffic amount. So if we take a like deeper look at what a shared nothing architecture is, so you can see, like for example, this SQL and the query plan for it. And as you may see, like orders have multiple partitions here, and the query will be split for like multiple scans, like those 3 partitions. And as each worker node is owner for each partition, the thing is each node should process only their own partitions and return as a result only aggregated data. So there is no need to like for router node to basically fetch any raw results from like this worker nodes. So and this allows you to like cut a lot of traffic like in terms of communication here. And for this real-time chunks, the example we just discussed, the pretty same way. If you can see here, there is like worker node 4 which is added, and for example we have orders and also union of orders, which is like orders RT real-time table, and those tables can be unioned together, and the query would be still the same. And even if we have union here and union basically on a partition side of things, this is this pretty same plan because optimizer knows it's like just one union, and it just split among nodes, and basically worker node that has mem table chunk, it basically merges it in flight, and results are returned that way. So again, there is no reshuffling or anything like it, so very efficient in terms of network communications. And yeah, the last one example really like just to continue this shared nothing architecture feature. So this is collocated joins, and collocated joins are also the way how you can do joins using shared nothing architecture. And it's basically the reason why we decided to go this way is because it's like really fast, it's distributed join algorithm, and it also can be used by other algorithms like shared nothing top K. And and we try basically to make all of our algorithms that are being processed in KubeStore being shared nothing, because it's really like a lot of gain in terms of performance here. And here you can see, for example, orders and users. If you want to join them together, they will have this shared index, which is collocated join index. And this is like a logical structure, and with physical partitions here on the side. And what happens under the hood here, when you are planning actual join, the magic here happens when actual distribution assigns node as an owner to basically process only corresponding keys or corresponding partitions here. For example, orders and users have a corresponding 1 and 4 on that working node 1, and 2 and 5 and 3 and 6. So this allows you to eliminate all key space intersections, which allows you to shared nothing join at that point, which is quite effective in terms of performance. So almost as the same effective as a like aggregation, like in general, because it's we use here merge join. So yeah, so basically another one application of shared nothing architecture, how you use it. Again, it's really like high level, I would say, design decision sneak peek. And if you want to learn more, just stay tuned and see our blog post in 2 weeks about KubeStore. So I hope it will share like a lot more detail, and I hope it was interesting. Yeah, thank you. I would love to answer your questions.
Thank you, Pavel. That's a great talk. There's a couple of questions queued up in the Q&A box. If folks have other questions, feel free to put them either in chat or Q&A. We have one here. Thanks for the talk. What's sub-second latency exactly? And I think I'm going to interpret this not as what is sub-second latency in general, but what do you mean when you get sub-second latency? How fast is it?
Yeah, so in terms of, again, so what is sub-second query latency? First of all, like, is a definition, is a time from, so like query latency in general is a time from like request started, like query started, right, to time it was fulfilled by KubeStore. it's basically a latency users see when they open in dashboard and their charts begin to show up. And sub-second means basically less than a second. And our target goal is like in range of 200 milliseconds. It's what we're trying to achieve for all of our queries, or basically P95 in KubeStore.
Another question, which may be from the same person: how can we try KubeStore?
Yeah, great question. Just go to KubeDev and get started. So it's open source. You can self-host it and basically use it, no strings attached.
I have a question while other people are thinking of things. So when I first approached this, I had the idea that you guys were sort of a pull-through cache where somebody would submit a query and then you would go fetch the data and then cache it. But that's not really how this works, right? You're you're actively, you have a SQL layer, which gives people a standard SQL interface regardless of where the data came from. And then you're actively populating the KubeStore. So can you describe a little bit what the development process is that somebody goes through to use this? That may be really explaining the model for Cube.js.
Yeah, this one is a great question. So so in terms of development process, we have this concept that's called data schema, and it is basically you're writing SQL queries to your data, which eventually will be like fact tables, and you define measures and dimensions the same way you're defining it in many popular BI tools. And at that point, Cube will provide you with an API layer. So all of business definitions you defined are in your API at that point. But the thing is, if you don't define so-called pre-aggregations, which are materializations from KubeJS standpoint, all the queries will go directly to data warehouse. It's something we started from, and it's exactly as you described it in a Cube. It's in its early days, so it's a caching layer on top of your data warehouse. But as we figure out and as we move this caching layer much further, we figure out that we need some kind of materialization layer, because people demanded it, how we can basically make it much faster. And again, we are talking here about sweet spot for Cube, which works on top of data warehouses, and most of our users are using data warehouse, and they use this ELT pipelines, DBT tools, and all of those piping technologies in terms of data loading. So at that point, we figure out how can we move it further in terms of performance, and it's how we ended up with KubeStore. Yeah.
One final question from my end. Do you have metrics available on KubeStore so that we can, so for example, it looks like you have a notion of a query plan. So so you've, and you can do an explain and see what's going to happen. But do you have metrics so that we can monitor the KubeStore and understand how to tune its performance and also keep it healthy?
Are you question about more about benchmarks?
These are operational metrics. So for example, what's the, because I can just picture a lot of different ways where if you didn't have data loaded correctly, or you were out of disk space, there's just all kinds of, low on memory. There's all kinds of ways that this could not be so happy. Yeah. How do you handle that?
Yeah, it's a great question. We do have these metrics. However, those are mostly done right now in Cube Cloud. So Cube Cloud is a hosted basically solution for KubeJS. So manage infrastructure for Cube and KubeJS, and also KubeStore. So it is provided as a serverless layer for your applications, and we have it there. We don't have it yet in open source, but it supports open telemetry. So you can connect open telemetry and see tracings, and you can set up your own monitoring infrastructure using APIs inside of KubeStore.
Great.
So we have it this one. Yeah.
Great. We've got a couple more questions that came up. Here's one from Vasevolod. Do you have a public roadmap for Cube.js, like what you're working on now and what's coming?
Yeah, we do. So if you go to Cube.js open source repo, so we have it on a projects tab, and we have roadmap there.
Great. A final question, because we're over time. How can we see which queries and pre-aggregations correspond to specific Parquet files?
Yeah, it's this one is a great question. So we have explained plan for that, and the only thing it's when you basically work in this cube store, there are logical plan and physical plan, and you basically want to see like physical plan. We don't have an actually like console, like CLI tool to see those, like in terms of we have for logical but not for physical, but it is shown in the tracing logs. If you like enable tracing logs the same way it's done in ClickHouse, if you enable it, you'll see tracing logs and it will contain these physical plans. But we are working on like providing basically SQL command to fetch this plan.
Pavel Tiunov, thank you so much for a great talk on Cube and Cube Store and the decisions behind it. Really looking forward to trying this out.
Yeah, thank you. Thanks.